So now we're going to talk about energy stored in a magnetic field. So we can use the loop rule that we were using previously based on this RL circuit, which I'll rewrite here. So we had the EMF equals L di dt plus IR. And essentially this equation is a differential equation that describes the growth of the current, which we can see with the di dt. So we can multiply everything in this equation by I, in which case we'll have EMF times I equals Li di dt plus I squared R. And this equation will have a physical representation of the work done by the battery and the resulting energy transfers. So we'll take this term by term. So we can say that the left side here, the EMF times the current, represents the rate at which the EMF device delivers energy to the rest of the circuit, because we have E times I, which is dq dt. And then this term over here, which is the I squared R all the way over on the right, is the rate at which energy appears as thermal energy in the resistor, because we're going to lose some of the EMF when the current passes through the resistor. So finally, this Li di dt becomes the rate at which magnetic potential energy is stored in the magnetic field, because due to conservation of energy, we need to store this energy as a magnetic field of the inductor. So we can write Li times di dt as the change in potential energy. So we'll have d magnetic potential energy dt will be equal to Li di dt. So after this, we can say that since we have dt for both, we can write that d potential energy equals Li di. And from here we can integrate. And our bounds here would be from 0 to the total potential. And over here our bounds would be from 0 to I. So after we integrate this, we'll have the potential energy is equal to, and we can use the u to the n du rule here, so we'll have 1/2 Li squared, and that will give us the potential energy that will be stored by an inductor carrying a current I.